on there. What we're looking at here is a pressure, temperature, temperature, phase diagram. Okay? And this is for most substances. Okay? Now what we're going to be looking at here is on this x-axis, and we could flip this if we wanted to, but typically, traditionally, you put temperature down here and pressure up here. Really, in this case, neither one of those is the independent variable, because either one of them could be used as the independent variable. You switch them around. But typically, traditionally, when you see these, they're done this way. So temperature goes down here. And since we're not going to have specific temperatures, and the temperatures are different for every substance, we're just going to say it's increasing going in this direction. Okay? And over here, we're going to say that the pressure is over here, but we're not going to have specific numbers. We're just saying it's going to be increasing in this direction. Okay? So, we take almost any substance, and we have a very, very low pressure and low temperatures, low pressures like, nearing nothing, no pressure at all, like out in space. Yeah. And if I am down in this range where I have low pressures and low temperatures, liquids don't exist. Where we have low temperatures and low pressures, liquids don't exist. Okay? So on this side of this positive sloped line, these are all solids over here. And gases are going to be over here. Okay? There are no liquids. So if I take water and put it in a cup and keep the temperature fairly constant, okay, and put it in a weather balloon or hang it on the bottom of a weather balloon and let it rise through the atmosphere, the pressure gets lower and lower and lower as I get nearer and nearer to space, eventually water will boil without ever getting to 100 degrees C. Water boils at a lower temperature in Denver, Colorado than it does here. Anybody ever read the packages about how to bake cookies or bake cakes, and it says you have to change how long you bake it based on where you are, what your altitude is? Okay? Same basic idea. Has to do with the boiling temperatures of water. If it boils at a lower temperature, you've got to cook it longer. Okay? So if you want to kill all the bacteria in your food before you eat it in Denver, you've got to boil it longer than you have to boil it here, because it boils at a lower temperature in Denver, because the pressure's lower. Okay? All right. Then we get to a point, if we raise the temperature and pressure, we reach this point here where we got the pressure high enough to actually have a liquid. Okay? So liquids are going to be up here in this part of the graph. And the boundary line between solids and liquids leans slightly forward. Slightly forward. Okay? Now what does that mean? Well, as long as I'm in this region right here, in between these two, along this edge, so here's what, if we're between here and say here in temperature, okay, in between there, if I increase the pressure, okay, I increase the pressure going in this direction, I can go from liquid to solid. So I can solidify something by increasing the pressure. Does that make sense? All right. Now, huh? Don't play with my stuff. Unless I tell you to play with it, don't play with it. Really, come on. It ain't your stuff. Alright. This line you don't have to draw. I'm doing it mainly to make a point here, okay? I'm putting a dotted line here. And the reason I'm putting this dotted line here is I want to show you that the curve I'm going to draw never goes downward. It's always sloping upward. It's always positive. And it's going to reach a point up here, and it never becomes perfectly vertical either. Okay? It's going to be a true function. Because a function never flips back on itself, right? On the right? Y'all remember what that is, a function? Okay, if you're taking math or somewhere later in math, you may hear the term function used by your teacher. Well, a function never flips back this way. It can flip down this way, but it can't flip back toward the y-axis. Okay? All right, so it's always going up, but it's going to curve upward like this. And it never goes perfectly vertical. So the boundary line between liquids and gases is not a straight line the way it is for solids and liquids. It's a curved line that's always having a positive slope and is always a function. When you say the opposite way, back to the left, it can't go back to the left. That's right. It's got to go up and to the right all the time, but it's still curving. Okay? All right. So, if I have a solid at this temperature right here, let's put the, top of the thing here, and I keep it, this is something you should know. You probably know this kind of stuff. Solid becomes a liquid as I heat it up some more, becomes a gas, right? That's the stuff you know. That's what we talked about in here already. Okay? The difference is how that pressure-temperature relationship actually works. Because around here, we just deal with about 1 atmosphere. The pressure doesn't change a lot. Changed a little bit. I've got a pressure sensor up here. I can tell you what the pressure is in the room right now. Okay? All right. But there is this sort of balance and relationship. Now, once we get to a certain point in temperature, there's this point in temperature where no matter how much pressure I put something under, I can no longer make a gas become a liquid. As long as I'm down in this range here, between here and here, if I have a gas and I put it under pressure, I can make it become a liquid. Does that make sense? If I'm under here, I'm going to get a gas at, say, this temperature right here, and if I increase the pressure, so I'm going to move it this way, it'll become a liquid. Right?
Okay, I have a question.
Okay.
So on the test, we have to know how to draw that, or
yes.
Be there for
You'll have to know how to draw it. All right. We talked about this yesterday, that if you have particles that are gas, they don't touch except to bounce around each other, bounce off each other, and you squeeze them down, squeeze them down, squeeze them down to the point where they're touching, it would seem reasonable they're going to become a liquid, right? Because that's what a liquid does. They touch but move around each other. Correct? Y'all remember that? You remember that? Because you aren't listening. You're talking to him. Make sure you listen. This is important. We're going to have a test on this tomorrow. All right? I'm not talking to you, no. He knows who I'm talking to. All right. So there's a certain point, though, where the temperature is so high, those molecules or particles or atoms or ions never stick together. You might force them to touch, but they never really stick, and so it never can be a true liquid. Unless they stick, they can't be a liquid. So up here, then there's this point where the temperature gets so high that we never can make a liquid. Okay? And once we get past that point, we don't have liquid anymore, and we don't really call it a gas anymore. We call it something else because it's in this special category. It has special properties. It do a lot of neat stuff for us. We call it a supercritical fluid. Supercritical fluid. Those supercritical fluids are really important. We were talking about carbon dioxide a while ago. They use supercritical carbon dioxide to remove the caffeine from coffee and tea.
So that right there is not a liquid.
It's not really a gas, not really a liquid. It's called a supercritical fluid. Fluids are things that can flow, and both liquids and gases can flow. Okay? And we call a supercritical fluid, I don't know why they give it supercritical, but that's what they call it. Okay? All right, so that's the supercritical fluid. It's an important category. That's why I want you to know about it. Okay?
Is
Now,
there not one for solids and liquids like our experiments we did? Remember
a point where you got it so hard it can't be a solid anymore? No.
No,
Oh.
our experiment we did on the first day.
Oh, yeah, that's a kind of a different thing. Okay, here we're talking about the relationship between pressure and temperature on a substance. Okay, what we dealt with on the first day, that substance is called a non-Newtonian fluid. Okay, and actually a non-Newtonian liquid. Okay, and I don't know if I've told you this or not, but that stuff, if you put it in a swimming pool, you can run across it. But if you stand still, you sink. Okay.
Yeah, the stuff like that.
Yeah. If you fill up a swimming pool with that stuff and you run across that swimming pool, you can do that. But if you stand still, you're going to sink.
Let's try it. Let's do it.
I can't afford the money to fill up a swimming pool with that stuff.
It costs like $200 for a little baby swimming pool.
Okay. It would cost, yeah, it costs. I did the math one time because my church for Vacation Bible School was doing a thing about, science stations, okay? And I said, man, this would really be cool for these kids, But I couldn't afford to do it, so, Anyway, all right. This point right here, let me back up a minute. If I take some ice is a solid, and I put it in a glass, and I leave it on my kitchen counter, and I come back 2 hours later, what's going to happen? It's all water, right? Okay. Suppose I come back before it's completely melted. I want to have ice and water in the same container. And if I measure the temperature, I'm likely to find the ice and the water have the same temperature. Because as long as the pressure is right here, as long as I'm right here in temperature, whatever this temperature happens to be, ice and water exist at the same time at the same temperature. Ice and water exist at the same time at the same temperature. Now what's really cool is when you get right here. If ice and water can exist at the same time at the same temperature, it turns out gases and liquids can exist at the same time at the same temperature. That's what happens when you boil water. When you're boiling water, if you measure the temperature of the steam, it has the same temperature as the water that's boiling. So if I'm right here, I can have liquid and gas at the same temperature at the same time. What do you think I can do right here?
You can have all three of them.
All three of them at the same time in the same place. Yeah, it's called the triple point.
Is that like, can you do that with ice too?
With what?
How ice is so cold that it has like the little stuff rushing up it.
Like the steam stuff, I was about to ask you about that.
Is that a demonstration of all three of them?
What's that?
You know how when ice is like really cold
Huh?
and you can see like the
Oh no, that's a whole different process. I got you. I understand. That comes from, well, let's not get into that right now. Okay? So this point right here is called the triple point. The triple point. Okay? Now, just for the purposes of clarification of terms, I want you to know that this line that's right here that separates solids from liquids, we call this a solid liquid phase boundary. Okay? And this curve right here, we call this a liquid gas phase boundary. I'll bet you can predict what we're going to call this. Right here.
Solid, liquid, gas.
Not solid liquid,
The
solid gas phase boundary, right?
on the liquid gas phase. Are you pointing at the little curved line?
Yep, that's the boundary between liquids and gases. Liquid gas phase boundary. Now you can reverse solid liquid or liquid gas. Okay, you could call it the liquid solid phase boundary. Wouldn't matter. Huh? There you go. Sorry.